Yes, today I would like to present on some exploratory study that we did on metal to glass bonding with a structural PVB. I present this on behalf of my colleague, Manuel Santarchero. He worked at Eckersley O'Callaghan at the time that we did the study. And on behalf of myself, and I worked at TU Delft at the time of this study. So what we are looking at today is, let's say, laminated connections. I think everybody is familiar with that. So we can make laminated connections connecting glass and metal through interlayers by embedding metal into a laminated piece of glass, using the interlayer to glue or to adhesively bond the pieces together. You can do that with a thick piece or with a thinner embedded steel piece. And on the right-hand side, you see also examples that you can laminate something on the outside of the glass. For instance, on the surface of the glass, but perhaps also at the edge of the glass. So in this case, we don't use adhesive, but we use the foil interlayers to make this connection between metal and glass. Just to show you some examples, this is a quite a renowned example, I think. In the Apple stores, there's quite a lot of lamination with embedded connections like here for the facade connections, but also embedded connections for the beam connections there. So this is then, for instance, laminated with Sentry glass. But you see them also in other projects appearing. Also here you see the connection between the glass facade and the glass fin. It's an embedded connection, as you can see here. 4 layers of glass, and this metal piece is laminated in between there. Apart from this insert connections, you can, as I said, also make point connections. This is again an example with Sentry glass for a staircase at the Glass Tech. So all these metal connectors are laminated to the glass using the autoclave process, again with Sentry glass in this case. There is also another product on the market, TSSA from Dow. It's a transparent silicon adhesive, by which you can make also point connections that you also laminate to the outside of the glass. You can see some examples here that you glue adhesively bond using this film adhesive. So just to set the scope a little bit of the presentation, what I would like to look at today is these two options, so that we embed something with a thin metal into the glass and that we externally laminate something on the outside of the glass. And we do that with, let's say, a newly appearing product on the market, a structural PVB from Eastman, Saflex DG 41. Which is a stiffer PVB than the regular PVBs. So we just did this exploratory study on how far, what are the potentials of this structural PVB to laminate, to glue metal to glass. We did 3 test series. On the left-hand side, the Pullout tests. I will start with that. In that one, we embed a very thin piece of metal into a laminated piece of glass. You can see that here. So this is laminated glass. This is going into the glass. It's a stainless steel, 25 millimeter wide. This length is 80, and on the opposite side we have a length of 40 millimeter embedded. So just to force that this will be the weaker spot of the specimen, and later we will pull out the embedded steel. And here you can see the cross section. You can see that we used 4 layers of structural PVB to reach about 3 millimeter thickness of the whole laminate. This is a test setup. We are then pulling the steel out of the specimen. So this is the glass. There we clamp the steel in this clamps, and then this one is moving up at a specific rate of 1 millimeter per minute. And we have performed these tests at 23 degrees without any temperature conditioning. So the fluctuation could be quite large, actually. So that's why there's let's say, a margin of about 3 degrees on this testing temperature. You can see the test here. I just show you some screenshots, let's say. So this one will be moving upwards, and then we pull out this one because it's a shorter length. And you will see delamination starts from the top there. So the metal is a little bit getting thinner, let's say, by pulling it. And then you see the delamination starting at the top and progressing downwards, again there, until we reach the full capacity of the specimen, and then the metal is put out of the laminate. You can see that again. So delamination starts there because of the necking of the metal and also the deformation of the interlayer. And then this is close to being fully filled. So these are the results. You can see the force, the pull-out force, and the displacement of the whole machine there. Quite good consistency in results. So every specimen has the same curve, let's say. This is the average pull-out load of about 16.4 kilonewton, which is significant. And you can also see that the standard deviation, the scatter in the results is quite small. So a very consistent result for these specimens. These are only 3 specimens at the moment because we are just exploring the possibilities. But nevertheless, it gives a good indication of the possibilities. The next test that we did was a shear test. In this case, then we laminated something on the outside of the glass. You can see the specimen here. So it's a fully tempered piece of glass, 50 millimeters thick. And then we laminated this stainless steel button on top of the glass using the structural PVB at this point. And again, we have used 4 layers of interlayer to reach 3.04 millimeter of thickness. And then we place it in this shear test setup. So we are going to shear the button, the steel button, from the glass piece. It's a bit difficult to see perhaps, but if we start on the right-hand side, you can see that here is the glass specimen inserted, and here's the steel button then going through this metal plate, and in the end this metal plate will move upwards to shear the specimen, to shear the steel button from the glass specimen. The glass specimen will move upwards, but it's blocked here by these by the setup there. At the same time, we are measuring the deformation of this steel button by these LVDTs that measure the relative displacement to the glass. So the local displacement of the button relative to the glass. We record the load at this side with a load cell of about 10 kilonewton. So the tensile force is exerted here, and then it's measured there. This is the same setup, but then from the other side. So now we look through the glass. You can see the metal button is laminated there, inserted there. It's blocked over there, and this piece will move upwards to shear the specimen. This is a video. In the beginning, you don't see that much happening. This is just to indicate that the force is moving upwards. You can see delamination starts there, and it's progressing upwards a little bit. Until we reach failure of the specimen, then you have complete delamination there. Here you can see it again, but then in pictures. So start from this point, and then it's progressing in this manner until we have full delamination there. These are the specimens after the test. So we tested 5 specimens in this case. You can see that for the specimens 1 to 4, we have adhesive debonding at the glass side. And for specimen 5, we even pull out the glass there. So we pluck the glass, so the top layer of the glass is completely ripped off from the glass specimens. So relatively high adhesion there. These are the results. So again, the force, and then the displacement of the button relative to the glass. This has some initial sediment of the test setup, so you can ignore that, but you can see that it's quite consistent again. We reach an average failure load of about 14.3 kilonewton. A little bit higher scatter, let's say, but still an acceptable number there. So still quite consistent results. And in this case, we have tested 5 specimens. Still not a lot, but enough to get a first indication. And then we did the last test series on tension testing. For this, we used the same specimen type. So again, stainless steel buttons laminated to a fully tempered piece of glass. Again, with the thickness of 3.04 millimeters. And in this case, then we pulled the bottom from the glass in this direction. You can see the test setup here. The specimen, the glass specimen is over there, and then the steel button is inserted through this hole, and then it's pulled by this the setup there. What we are measuring actually is, you can see that on the other side, with these 3 LVDTs, we are measuring the relative displacement of the bottom compared to the glass again. So we can also measure the inclination there. We do that again at a test speed of 1 millimeter per minute, and again at a non-conditioned temperature of 23 degrees room temperature. This is the test setup, just a short video. You don't see that much happening. There's also no sound, but at the end you see that the piece comes down from the metal button there. Again, the 5 specimens that we have tested, you can see delamination there for all the specimens at the failure load. These are again the results. So specimens go up until they have this ultimate failure load where they fail. This goes back to 0 directly, but the scale is so small, let's say, that you don't see that it goes to 0. But this is really the ultimate load that we apply there, could apply, with an average. With an average load of about 17.5 kilonewton. In this case, we had a quite high scatter of 24% standard deviation, and we think that's mainly because there was some inclination of the button on the glass. So then you are not pulling it evenly, let's say, so you have a specific stress concentration from which the failure will start. So we have investigated these 3 options with this structural PVB. So just to give you a discussion, it's of course difficult to relate if I say 14 kilonewton or 50 kilonewton, what that actually is. So just I would like to give you a short indicative comparison with other products on the market. So this is the result that we got from the Pullout test for the DG41, about 16 kilonewton, quite consistent results, very small scatter there. Unfortunately, we didn't do tests on other materials, so we cannot compare it, but for the shear test we could compare it. So we see for the structural PVB quite high shear resistance there, relatively acceptable scatter, small scatter. If you compare that, for instance, with TSSA, we did the same kind of test with TSSA, but then at a different machine, different conditions. So you have to be careful with this, with interpreting this. And also different thicknesses of interlayer, of course. So just want to mention that. Then you can see that it's a little bit higher than that. Also, TSSA shows whitening, as you might know, at a certain load, which is about 50% of this load. The same test for centric glass, again with a different thickness, so you cannot perhaps directly compare it, just to give an indication. And you can also see that centric glass also shows this relatively high scatter in this, acceptable scatter in the results there. And this is then for the tension results. Again, if you compare it to other materials, you can see quite high scatter there, but we think it's due to the inclination, as I said. TSSA has this value, and centric glass has this value. You have to be aware, of course, that for instance, centered glass, this value will go down quite significantly for higher temperatures because it's a viscoelastic response there. For TSSA, these values are quite stable because they are less temperature sensitive. We don't have yet information about the temperature response of the structural PVB, so that's why we should do more testing here. Nevertheless, you can see that the structural PVB has a good performance and can compare to other materials on the market there. So if we then look at the conclusions, the Pullout test had a reasonable failure load and a very high consistency there. Also, the shear test had a good shear resistance and a good consistency of the test results. For the tension test, we saw some more scatter there, but still a significant tension capacity. So overall, we can conclude that the metal-to-glass bond strength of structural PVB is significant and to be considered. And I think you can use it for specific applications within the engineering possibilities. Of course, we need to do further research because this was just an exploratory first study. Effects of temperature, load duration, and loading rate should be investigated, of course, due to the viscoelastic properties of the material. Aging and humidity we would like to look at, and of course, we have to increase the number of specimens because the number that we tested for this research was quite limited still. I would like to acknowledge all the support that we got, of course, from TU Delft, where we did the testing, from support from Kees Baardolf and Fred Schilperoort to perform the test, but certainly also from Eastman in providing the specimens and making the specimens, and also Wim Stevels for providing technical input and support. Well, then we come to almost the last slide. I moved to TU Dresden, as you might know, so this is our group. If you would like to visit that, you're certainly welcome, either in person or in the digital environment. Please look us up and join us for a visit. And just to announce that we are again preparing the Challenging Glass Conference for next year, 2020. This time again in Ghent University, together with Professor Baylis, my colleague from Eindhoven, Freek Bos, and myself will do the organization. If you're interested in presenting or attending or sponsoring also, you're certainly welcome to discuss with us. Thank you very much for your attention.
All right. So thank you, Christian. Do we have any questions?
Hello, Christian. I would like to know how where the delamination falls within these strength values, because I suppose whenever you have a customer and to assemble these bits, the aesthetic is crucial. So clearly the design has to be done within levels where delamination does not occur. So do you know where aesthetic remains acceptable within your data there in terms of failure?
Okay. I think I know what you mean. Can I still move it? Can I have the presentation again? Yeah, okay. I think you are asking for when the first failure starts to happen. So here, for instance, you see until 10 kilonewton, you would not see any visible indication there, I would say. So certainly until 10 kilonewton, you can use it without having a visible deformation there, let's say. But it depends, of course, a little bit on the testing, different testing methods that we used. Yeah.
I think in general it's very useful to have this data also if you want to know where the
Yep. Yeah, so you want to know in this graph especially where the first delamination started. Yeah, yeah. Yeah, yeah.
I had a question on,
No.
did you ever do some modeling to have an idea about the debonding energy?
I cannot see who's talking.
Sorry.
Oh, there, yeah, okay.
Yeah. And if so, did you see a difference for the debonding energy for shear and traction?
No, we didn't do that yet, no. So as I said, it's a very first exploratory test. Yeah, that's something we would like to do and also compare it to other materials, but at the moment, not the energy, no, no. Yeah, you can, of course, calculate some sort of average stress from this, but that's very indicative and I would like not to... Sorry.
Well, I think that you have to also deal with the viscoelastic properties of the material so that the modeling will be needed to see how much energy is going to the formation of the PVB or of the other materials and how much is going to the debonding of the material from the glass.
Yeah. For the Pullout test, there is quite a lot of deformation of the metal indeed. For the metal buttons, these are quite stiff and rigid, so there's not that much deformation of the button itself, let's say. It's also quite a thick button, so yes.
Thank you, Christian. That was a very interesting presentation. Quick question on design values, really. What would you recommend? You know, as a practicing engineer, I want to know what shear stress, what tensile stress to use for these materials for short-term, long-term loading?
Yeah, so all the testing that we did was short-term, so within 1 minute failure, let's say. If you calculate the average stress, then it would be around 7 megapascals.
Yep.
But you have to be very careful because that will drop for higher temperatures and for longer load duration.
Okay.
And also average you cannot really calculate with. I mean, it's always the peak value that is critical in this case.
Okay.
We did not do the numerical part yet of this. We can only do that if we have more specimens tested so that we know that these results are consistent. Yeah.
So it's work in progress rather than conclusion.
Yeah.
Okay. Okay.
Okay, any further questions? No? If not, thank you. Thank you very much, Christian.
Thank you. Pleasure.
Hi there. Did you like what you just saw? If you did, why don't you like the video, drop us a comment below, and share the video as well, since GPD is all about sharing. And to receive more videos in future, subscribe to this channel and don't forget to click the bell icon. Ciao!